Assalamu alaikum. This video inshallah will be the last part of tutorial 1 about closed system problems in Exergy chapter. In this question we have an iron block of unknown mass at 85 degrees Celsius. So the temperature of iron is 85 degrees Celsius and in Kelvin is equal to 358 Kelvin. Is dropped into an insulated tank, so there is no heat transfer in or out. Of course, it is a closed system that contains 100 liter of water, so the volume of water is 100 liter. If we divide it by 1000, we will get 0.1 meter cubed of water at 20 degrees Celsius. The temperature of water is 20 degrees Celsius and in Kelvin 293 Kelvin. At the same time, a paddle wheel, this one, driven by a 200 watt motor, is activated to stir the water. So the motor is rotating this paddle wheel, and paddle wheel is providing at the end or converting the power from the motor to the water and stir the water. So this one it is in watts, so it is a power, so it is W dot paddle N, because it is an input power. It is observed that thermal equilibrium is established after 20 minutes. So thermal equilibrium means the temperature will be the same. يعني the temperature of iron and the water will be the same. At the initial state, the temperature of iron is 85 degrees Celsius and the temperature of water is 20. After 20 minutes, so delta T equal to 20 minutes. If you multiply it by 16 seconds over 1 minute, it will give us 1200 seconds. With a final temperature of 24 degrees Celsius. So at the end, the final temperature T2 of water and T2 of iron will equal to T final, and this T final is 24 degrees Celsius or 293 Kelvin. So it will reach a thermal equilibrium. They will have the same temperature at state 2. Assuming the surroundings to be at 20 degrees Celsius, so T naught is 20 degrees Celsius. Determine the mass of the iron block. So he wants me to find part A, the mass of iron. And in part B, he wants to find the exergy destroyed. The special thing about this question that we have iron and water, liquid and solid. In previous questions, we solved about refrigerant, we solved about steam or water alone, about ideal gases, but we didn't have solid in the questions. Okay, so let's see how we will solve this question. He wants the mass of the iron. We will do an energy balance around the system, the whole system. Okay, so En minus E out equal to delta E system. The system is stationary and there is no elevation or velocity. So in delta E we will have only delta U, but we have two materials, we have two substances, we have water and iron. So we will have delta U for iron plus delta U for water. Okay, we don't have anything outside the system going outside. There is no work outside. Of course, it is insulated, so there is no Q out or Q in. But we have the paddle work in. So we have the paddle work in. This paddle work, we can find it because we have the power and we have the delta T, the time. So work بدل N is equal to the power times delta T. The power is 200 watt and delta T is 1200. It will give me joule, but we usually use kilojoules, so it's equal to 240 kilojoule. Okay. For the delta U iron and delta U water, we will substitute like the ideal gas, but now it is not CV or CB. There is no CV or CB. We only have C iron. T2 iron minus T1, but T2 for both is what is T final. So T final minus T initial for iron, it is T1 iron, or we call it T iron خلاص, plus M, of course this M iron, that is the first requirement from us. Okay, that is M water, C water, that is C iron, delta T also T final, it is the same for both, minus T water. I want to find M water. I already have work بدل N, I calculated it from a second. T final, I have T final, I have T iron, I have T water, I have T final, but I don't have M water and I don't have C water or C iron. We can find C water and C iron from table A3. Why table A3, not why not table A2 as the previous questions? This one for gases, we have liquid and solids, and this is for various temperatures and for only gases. Here in table A3 for liquid and solids. Okay, for water, we have water at 20 degrees Celsius. It is not here the 20 degrees Celsius, but we will assume it it is 25, because you can see that there is nothing difference between 1997. So if we made interpolation, we are wasting our time. So we will take approximately 997 to be our density, and for CV it will be 4.18. Okay, it doesn't matter. If you say 20, it will also get 4.18. Okay, why I'm taking density now? Because we will need it, because we want to find also the mass of the water. I have the volume of the water here, and we usually use M over V. V capital over V small, the volume of the specific volume, and the specific volume is the inverse of the density. So we can say this equation can be written as V in meter cube times rho. Okay, of course that is the volume of water, that is the specific volume of water, that's rho for water. Okay, so I can find the mass of water. The mass of water, we have the volume is 0.1 times the rho, it is 997. This will give me 99.7 kilogram, that is the mass of water. For CV, we say that it is for water 4.18 kilojoule per kilogram Kelvin. Okay, for iron, that is metal, non-metals. For iron, we only have this value. It is 0.45 for specific heat. So C, or CV or CV, it doesn't matter here. C iron is 0.45 kilojoule per kilogram Kelvin. Okay, so now I have everything. C mass of water, I got it. C iron, I have work Vn. So I will find the mass of iron. So let's substitute in this equation. So 240, that is the work بدل N, equal to M iron times 0.45 specific heat of iron. T final is 24 minus 85 plus 99.7, that is the mass of water, times 4.18, the specific heat of water, temperature difference, T final minus T1 for water. This will give me M iron equal to 52 kilogram. That is for the part A. For part B, he wants X destroyed. X destroyed. X destroyed, the easiest way is to use T naught S generation. And S generation is in entropy balance. S in, S out. This insulated system, there is no heat in or out. And of course, this is a closed system, so there is no mass transfer, mass flow. So there is no entropy transfer with heat or mass, and entropy transfer with work is 0 already. Okay, this 0, 0 plus S gene equal to delta S capital system. So S generation is equal to M. Let's write first, يعني delta S system, we have iron and water, so it is delta S iron plus delta S water. Okay, and we can write it in specific per unit mass, يعني M iron S2 minus S1 for iron plus M water S2 minus S1 for water. Okay, we assume that is it is a liquid or solid. Okay, for liquid and solids, we use this equation for solids and liquids. S2 minus S1 is directly equal to C ln T2 over T1. Okay, so for delta S iron, delta S capital iron, this one, this is equal to M S2 minus S1, so I will substitute M. And instead of S2 minus S1, I will write CV ln T2 over T1. C ln T2 over T1. T2 is a T final, and T1 is T iron at the beginning. Okay, and for water, this M, for this M iron, C iron, this M water, C water, ln T final over T water. Okay, then I will substitute, will be 52 times 0.45 specific heat of iron, ln 297 over 358 equal to negative 4.371 kilojoule per Kelvin, because it is not specific, that is entropy يعني itself, not per unit mass. Okay, 99.7 times 4.18 ln T final in Kelvin, 297 over 293 equal to 5.651 kilojoule per Kelvin. So X destroyed, which is equal to T naught S generation equal to T naught delta S iron plus delta S water, and it is equal to 293 minus 4.371 plus 5.651 equal to 375 kilojoule. That is for this question. Let's see the other question. He said a piston cylinder device. So we have a piston cylinder device initially contain 1.4 kilogram, M 1.4 kilogram of refrigerant, so R134A. So we are predicting that we will use the table of refrigerant at B1 100 kilopascal, T1 equal to 20 degrees Celsius, and equal to 293 Kelvin. Heat is now transferred to the refrigerant from a source. So heat is transferred, so we have Qn transferred at T source, or T at the boundary of the system. Sometimes we call it TB, and it is N, so TBN, 150 degrees Celsius, and this in Kelvin equal to 423 Kelvin. Okay, and this piston, which is resting on a set of stops, this stops, so it cannot move down more than this figure, starts moving when the pressure inside reaches 120 kilopascal. When it reaches 120 kilopascal, it will start move. So before 120 kilopascal, it will not move. Yani 119, it will not move. So after it will reach 120 kilopascal, it will move with this pressure, with 120 kilopascal. So that is P2, 120 kilopascal. Heat transfer continues until the temperature reaches 80 degrees Celsius. So T2 is 80 degrees Celsius. Assuming the surroundings to be 25 degrees Celsius, that is 298 Kelvin, and B0 100 kilopascal. Determine the work done. He said he didn't say maximum or minimum, so it is the actual work. Usually we use for the actual work the work that in the system, not the reversible work, not useful work, the work in the system. You cannot see any work. We see Q, but Q it is not a work. For a piston, we always say for a piston that is moving, it is have a moving boundary, so we will have the boundary work. So he is asking for the boundary work, and boundary work out, because it cannot go down, it will expand after it heats the source. This Q heat the refrigerant, it will expand and the piston will rise up. Okay, so work boundary out is needed. So, and work boundary out is B2, because it will be at a constant pressure, quasi-equilibrium process at B2, because B2 will start, the piston will start move with B2 after it reaches 120 kilopascal. So B2 times the volume difference V2 after it reaches up, or go up, minus V1 at the initial, this one, at this brown piston. Okay, but we don't often deal with the volume itself in meter cubed. We use the specific volume. So volume is equal to m times the specific volume, the mass times the specific volume. So we will write it like m b2 v2 small minus v1 small. That is for boundary work, but I don't have the v2 or v1. Do I have the mass? Yes, he gave me the mass, but v2 and v1 I have to find it using the b2 t2 and b1 t1 from the refrigerant table. So b1 t1, b1 is 100 kilopascal and also equal to 0.1 megapascal if you divide by 1000. Okay, and T1 is 20 degrees Celsius. Okay, so we want to find V1. Okay, and at the second state, P2 is 120 kilopascal and equal to 0.12 megapascal, and T2 is 80 degrees Celsius, and we want to find V2. Let's see if we want to find other things or other properties for if we saw the second requirement, part B or part C and part D. In part B, he wants to find the heat transfer, Qn, To find Qn in the previous questions, we usually used to do the energy balance. So En minus E out equal to delta E system. We have any work in, but we don't have any work in, but we do have the Qn. That is the one that we want to calculate, Qn. We don't have any Q out or work. We have work out, which is the boundary work that we will calculate in the first part. So we have the boundary work, P out. Delta E system, the system is not moving, it is not at an elevation, so delta KE and delta BE will be cancelled. So we'll have only delta U. Okay, so Qn minus boundary work out. Delta U, we usually write it like M delta U small, specific internal energy, and is equal to M U2 minus U1. So we need also to find U2 and U1. So we will write here that we want to find U1 and U2. Okay, let's see also the third part, part C. He wants to find the Exergy destroyed, X destroyed. There's usually T naught is generation. S generation is in the entropy balance, Sn minus S out. I don't have any heat transfer out. Of course, there is no mass transfer because it's a closed system. There is no work with the entropy. There is no entropy transfer with work. So there is no out, S out. But in Sn, I have heat transfer in. So I will have entropy transfer in. And entropy transfer is Q over T. Q, it is this Qn that we want to find in part P. And for T, it is a T of the source, T 150. So it is the Q comes from this source. So we'll write the temperature of the source, T source. Okay, plus S generation. Okay, that is the continue of the entropy balance. S generation equal to delta S system. S generation equal to delta S system is usually we write it in the per unit mass and we'll multiply by the mass. S2 minus S1 is small يعني. We want to find S generation. We already have T naught. So S generation will equal to M S2 small minus S1 minus Qn over T source. So also I want to find S2 and S1. So I will write S1 and S2 I want to find. For the last part D, the second law efficiency, I don't think you will you will need the table or you want to find anything other than these 2, 3 for V and U and S. So let's go for the tables, the refrigerant tables. Refrigerant table, table A12. We have at pressure P1 100 kilopascal. So 100 kilopascal. My temperature at this 100 kilopascal is T1 equal to 20 degrees Celsius. 20 degrees is higher than the saturation temperature at 100 kilopascal, so it is a superheated state. So I have to say that Tsat, saturated temperature, saturation temperature, is equal negative 26.37, and it is less than my temperature T1 20 degrees Celsius, so it is a superheated state. Okay, so I have to go to table A13. At 100 kilopascal is 0.1 megapascal. So 0.1 megapascal, you divide by 1000 at 20 degrees Celsius, and I will get these values S, U, and V. Okay, so V1 will equal to 0.23373 meter cubed per kilogram U1 will equal 248.79 kilojoule per kilogram, and S1 will equal 1.09 small يعني kilojoule per kilogram Kelvin. Okay, for state 2, I will go to 120 kilopascal at table A12. You always go with table A12 if you have the pressure. Then you will see if it is okay. I will get the value from here if it is mixture, or I should go to the superheated. And if it is subcooled, it is usually you will use you will assume it is a saturated liquid and use every properties in liquid state, يعني in F fluid. Okay, here we have 120 kilopascal. Okay, 120 kilopascal, and at temperature 80 is higher than negative 22.32. It is also a superheated state. So T saturation is less than T2, negative 22.32 degrees Celsius is less than 80 degrees Celsius, so it is superheated. Okay, so we will go to the superheated table. At 0.12 megapascal is not here, but it is between 0.10 megapascal and 0.14 megapascal, and it is exactly on the middle. Okay, it is exactly on the middle, so it is here. So here it is 0.12 megapascal. So if I take the at 80 degrees Celsius, okay, here, if I take the specific volume at 0.10 and the specific volume at 0.14, add them and divide, I will get the average. The average will be 0 for the 0.12 megapascal, and I will do the same with U and with S. Okay, at 80 degrees Celsius. So let's write this equation. So V2 at 0.12 megapascal and 80 degrees Celsius is equal to V at 0.1 megapascal plus V at 0.14 megapascal over 2, of course at 80 degrees Celsius, and U2 at 0.12 megapascal and 80 degrees Celsius will equal also U at 0.1 megapascal plus U plus U at 0.14 megapascal over 2, and also for S it will be the same. S2 at 0.12 megapascal and 80 degrees Celsius is equal to S at 0.1 megapascal plus S at 0.14 megapascal over 2. And you will get the values from here, this line. Okay, for S, U, V, S, U, V, and divide by 2. So let's write this down. Okay, 0.28465 plus 0.20242 over 2. This will give me 0.243535. And the answer in the solution manual is wrong. They took the not at 80 degrees Celsius, they make it between these two at 70, so the answer is wrong. Okay, meter cubed per kilogram, and for U it is 297.08 plus 296.75 over 2 equal to 296.915 kilojoule per kilogram. And for S So you can see for S I will take this value 1.2572 and 1.2288 and divide by 2. 1.2572 plus 1.2288 over 2 will give me 1.243 kilojoule per kilogram. So now let's find the requirements. So for the boundary work, that is the equation. So boundary work equal to m b2 minus v1 will equal 1.4 120 the pressure, the second pressure, the piston start to move with the second pressure. V2 is 0.243535. In the solution manual you will find it a wrong number, minus 0.23373 will give you 1.647 kilojoule. For the second part, Qn, let's go here. Qn equal to m u2 minus u1 plus the boundary work 1.4, that is the mass. Okay, 296.915 minus 248.79 plus the boundary work we got in the first part, it is 1.647. This will give me 69 kilojoule. Okay, that is for Q. And then we will go for entropy. Entropy. Okay, that is the equation for entropy. Because we want to find the X destroyed. So X destroyed is equal to T naught S gen, and S generation is already this equation. So it is M S2 minus S1 minus Qn over T source so let's substitute. T naught is 298, 1.4, S2 is 1.243 minus 1.0918 minus Qn 69 over T source 423. This will give you X destroyed equal to 14.47 kilojoule. Okay, for the last part, he wants to find the second law efficiency of this process. Part D, second law efficiency, is equal to the general equation for the second law efficiency is X recovered over X expanded equal to 1 minus X destroyed over X expanded. Because the X recovered is equal to X expanded minus X destroyed, then X expanded over X expanded will give you 1, and the remaining will be minus X destroyed over the X expanded. Okay, what is the meaning of X recovered? What is the meaning of X expanded? Recovered means يعني the useful work that you benefit from it, يعني the useful work that you can use as a potential to do work. يعني for example, this heat is not a work recovered. We lost this heat, we heated the refrigerant by this heat, okay, but the actual work was produced by the boundary work. Okay, so I didn't benefit from the Q itself, so the exergy from this Q is an expanded exergy, but the increase in exergy يعني from state 1 state 2, even if it is not mentioned here or if it is not required from us, the increase in exergy delta X from state 1 to 2 is a potential work, or a work that is recovered for me. I benefit from it. So you always see what you benefit from it and what it is lost or expended. يعني for example, if we saw the summary for heat engines, the exergy expended is a decrease in exergy of heat transfer to the engine. Okay, يعني الهيت engine is taking Q heat from a high temperature reservoir and rejecting heat QL, this QH, to a low temperature reservoir and producing work. Okay, producing work. This heat, I'm not benefit from it. It is just going to the heat engine. I am benefit from the work out. So the exergy of this heat minus the exergy of this heat QL, the decrease in exergy of the heat transfer to the engine, which is the difference between the exergy of the heat supplied QH and the exergy of heat rejected QL, is the exergy expended. But the recovered exergy, what I benefit from it, is the network output, this work out. Okay, for refrigerators it is the opposite. For refrigerators you you take input work. يعني if you draw a refrigerator here, refrigerator, okay, you take input work in, okay, this work in, and this one is QH, I think, and you produce QL. The benefit, or what is the benefit of refrigerator, what is the job of refrigerator, is to cool the medium, is to cool the room, is to cool the food. So the benefit is QL. So QL, the recovered exergy, the exergy of the heat transfer from the low temperature medium for a refrigerator. I don't think that I wrote it right. Yani maybe that is that's QL and that is QH. This one that you benefit from it. Yani you're taking Q from the for example, for the refrigerator, when you take Q out, you take heat out, the food will cool. Okay, you will cool the food. It will have a low temperature. So QL, what you benefit from the refrigerator is QL. That is the recovered exergy. The expended exergy is the work input. You are not benefit from it like the heat engine. You are consuming work. You are consuming electricity to make the refrigerator work. So think about it like it is what I benefit from it. It is recovered exergy. What I consume or I lose, it is exergy expended. The same thing for heat pump. For heat pump, from its name, heat pump, it pump heat, so it is QH. Okay, and take work input and take work input, yes, and take QL, I think, yeah. Because I didn't revise this topic, but يعني in general, QH is the benefit that you take from the heat pump. Exergy, the recovered exergy, the exergy of heat transfer to the high temperature medium for a heat pump. The exergy expended is the work input. You are consuming work to make the heat pump work. يعني think like this. In our case, also يعني you will find for the work producing devices like turbine, for work consuming devices, يعني I wrote for everyone in the summary. For steady flow devices like turbine, compressor, you have heat exchanger. There is maybe 3 or 4 cases for heat exchanger. You have mixing chamber. So read this one. Okay, returning to our problem. So where is the equation? So here we have Qn. So Qn, I didn't benefit from the Qn. It is like a heat engine. I take Q, okay, I produce the boundary work, but Q, I didn't benefit from the Q. So what is the exergy of the Q? We are not saying that Q, it is the exergy expanded. The exergy expanded of heat transfer is the exergy expanded. يعني I'm not okay. Let's see. يعني you understand. Okay, inshallah. So what is the exergy of a heat transfer? So you have exergy with transfer, for transfer mass, transfer work, transfer heat. Here you will find exergy transfer. Exergy transfer by heat, that is the equation of exergy transfer by heat, almost like this. So you are assuming that you have an heat engine, a reversible heat engine. Reversible heat engine have an efficiency 1 minus TL over TH. Here we will use TL as the surrounding T naught, and TH is our source, the source that produces the heat. So T source in our problem. Okay. Entropy transfer by heat, we use it in the entropy balance, S heat equal Q over T. If you have not constant temperature or variable temperature, variable heat transfer, you will use this equation, but not often we use it. We use usually this heat transfer for exergy transfer by heat. Exergy transfer by mass is also equal to m times the exergy. This you will find it in the open system. We will not find it here. Okay. Also exergy by work, transfer by work, we have the work surrounding, this was the similar to the useful work. Okay, we have the work minus the work surrounding. So here only we have the heat transfer in our problem. Okay, so we will say that X expanded. I will not write with this on. Okay. X expanded, or X expanded, yes, is equal to X Q, or X by heat, and is equal to, as we can say, it is the efficiency of a reversible heat engine times Q, and here we have Qn. So we write it like 1 minus reversible heat engine means follow the Carnot cycle, so 1 minus T naught over T. Here it is T source, it is the highest temperature source, okay, times Qn. Okay, let's substitute. So X expanded is equal to 1 minus 298 over 423 times 69 and equal to 20.39 kilojoule. Of course, the numbers will be different from the solution manual because they made a mistake in the specific volume V2, I think. Okay, and we have the exergy destroyed. So we calculated in part C, so we will substitute in this equation. So second law efficiency is equal to 1 minus 14.47, that is the exergy destroyed, over the exergy expanded 20.39, which is equal to 0.29 and equal also to 29%. We can also find the second law efficiency by another way. We can use this equation. Okay, let's see here. We have the exergy expanded, it is the XQ, X heat, but what is the exergy recovered? Exergy recovered is the delta X, or the change in exergy from state 1 to 2. It is an increase in potential, useful potential work. So it is a benefit for us. I can recover it. I can already I use it, or I recovered it. I don't know. So also we have the useful work. The useful work is have an equation here in the summary. Useful work is work minus the surrounding work, and it is in this work, note that the work done by or against atmospheric pressure has a significance only for system whose volume changes, like piston cylinder, during this process. System that involves moving boundary work, the same like our problem. So we have a moving boundary works, we have a boundary work. So this W in this case, in this problem, will be the boundary work minus the surrounding work. It is this equation. Okay. So delta X plus W useful will give you the X recovered. Okay. So let's find delta X, and let's find delta X. Delta X is M phi 2 minus phi 1 is equal to M U2 minus U1 minus T naught S2 minus S1 plus B naught V2 minus B1. Okay, this is equal 1.4 to that is U2 296.915 minus 248.79 minus T naught 298 times S2 minus S1 1.243 minus 1.0918 plus B naught is 100, V naught V2 is 0.243535 minus 0.2373. Okay, this will give you delta X equal to 5.667 kilojoule. For the useful work W, we will use the equation W minus W surrounding, and here W is the boundary work out. Okay, boundary work out we calculated, its value is 1.647, and work surrounding, we knew that the work surrounding is equal to B naught, the change in volume, times the change in volume, but we don't deal with the volume itself, we deal with the specific volume. So it will be V2 minus V1. And so let's write it here. So minus M is 1.4 times 100, 0.243535, that is the V2. I'm writing this equation in here. Okay, minus 0.2373. Okay, this will give me the work useful work useful out will be 0.2743 kilojoule. Okay, if I add both of them, X recovered, they will give me X recovered 5.667, that is the change in exergy, plus 0.2743 equal to 5.9413 kilojoule, and the second law efficiency will be X recovered over X expanded, that is 5.9413 over X expanded, which is the X expanded is from heat transfer, exergy by heat, this one 20.39. This will give me 0.29, which is equal also 29%, and you can see it is the same number here. So either way, you can find the second law efficiency from this two methods. And now we already finished the tutorial 1 about the closed system. Inshallah, we will have tutorial 2 about open system and steady flow devices, inshallah. Thank you.